sampling via approximate symmetries. Okay. So the problem we're trying to address is the sampling from a multimodal distribution. So here I use PS to stand for the distribution where S is a state and P is the probability. And the one thing that's going to play an important role here is something called log density. Log density, you can think about just the log of P up to a constant. So P is proportional to log of exponential of this E. Now, for those in physics, typically you don't like to work with log density. You like to work with the potential energy. So this E is actually the minus of the energy, if you like to think about this. Okay. So it has a lot of applications in statistics, in statistical mechanics, in probability, and sampling a multimodal distribution is very important. So there are a few challenges in sampling a multimodal distribution. And the first one, which is not really a challenge, I mean, but needs to be addressed, is that within each mode, sorry, that's not mode. Within each mode, you actually have to mix rapidly, okay? And the second thing is that you typically need to discover new mode and jump to the new mode, because otherwise you're not going to be able to sample some other important part of the probability. Sorry for the typo, this should all be modes, okay? And finally, that you also have to balance the frequencies that you visit different modes, okay? So these are the important things we need to ensure if you want to be able to sample multimodal distribution efficiently. Okay. There has been a lot of work on that. I mean, I'm just highlighting a few important directions and areas. So the first area is the so-called multi-level tempering and also continuation method. The typical idea here is that you start changing the temperature. So when the temperature is really high, corresponding to the inverse temperature of beta, which is close to 0, and then the distribution itself doesn't have a lot of modes. It's kind of like flat. So therefore, a typical algorithm like Langevin and also Gibbs sampling, they can sample quite efficiently. So the idea is then do a continuation from the target temperature, which is beta equal to 1, inverse temperature beta equal to 1, all the way to beta equal to 0. And then you sample different levels and try to jump between different levels to sample the target distribution where equal to beta equal to 1. So there are many examples here, simulated tempering, parallel tempering, annealed importance sampling, and temporal distribution, temporal transitions. So I'm going to touch on to two of these examples later on. There's annealed importance sampling and temporal transitions. But the issue with this continuation method is that the target distribution when beta is equal to 1 and also the nice distribution when beta equal to 0 are typically very far away. So therefore, you need a very long continuation path to go from one side to the other. Okay, so that's why sometimes it's not very efficient. Now, there's another kind of system which is fairly easy to sample just by coincidence, you can say, is that if the system itself has some symmetry in it, then it's very easy to sample. So for example, you know, if for spin Ising models, the spin all 1, all plus 1, all minus 1, they have exactly the same probability. So therefore, you can jump from one to the other by doing a global flip. Okay, so when this happens, it actually makes the different modes very rapidly. So some examples here, for example, Swenson-Wang. So if you're familiar with the Swenson-Wang, you'll remember that it has this global flip, kind of like for a large chunk of spins. And also in some sense, this Hamiltonian Monte Carlo, which is sometimes also called hybrid Monte Carlo, it also has this flavor because this Hamiltonian flow itself is actually a symmetry on the probability distribution. Okay. So now, but these things come in very rare, all right, symmetrical systems. So you might ask, I mean, how fragile this is? I mean, can we do something a little bit more general? Well, so the question that we're interested in this project is that what if this distribution actually is approximately symmetric, so it's not exactly symmetric, but close to symmetry. Can we do something? Okay. So this is the topic of this project. So it has three parts. One is I will talk about the main idea. This is the most important part, and I will go into a little bit detail to see how do you actually combine these main idea with the continuation methods I talked about. And finally, I will just give you one example. Okay. Hopefully, I'll have enough time. All right. So here's the definition. What do we mean by distribution symmetric? The distribution symmetric is that if there's a group G, capital G, such that for any group element, lowercase g, such that you apply the G to the state, it moves to a new state, and the log density over there is exactly the same as the log density where you come from. So in some sense, this group G itself is actually is invariant action on this log density. Okay? So once you have this this nice thing, which is invariant, then you can introduce this very simple transition. This transition is the following, is that so given a state S, you're going to go to T, a state T, if T is actually on the orbit of this S. Okay? And you actually, what you can do is that you go to any member on this orbit with the probability 1 over the cardinality of the group minus 1. Okay? And for all the other members, you just don't go there. Okay? So this allows you to jump between different modes. And this satisfies detail balancing because the original probability itself is symmetric. Okay, this is why the the symmetric distribution is easy to sample because this group action is bring you from one mode to another. Now, what if this is not exactly true? We say that the probability distribution is approximately symmetric if such that the group action on the log density is in fact is roughly true, but not exactly true. Okay? So this is not a very precise statement, but I hope you get the idea. Now, how do we handle the, this is the most important slide. So how do you handle the approximate symmetric distributions? The idea is very simple. So all you have to do is that you average over the orbit, right? So you take the log density, and then what you do is that you average over the whole orbit, and the average of this is guaranteed to be symmetric. It's just by the first thing you learn probably in group theory. Now, so this log density, which I got by averaging over the orbit of the log density, I call the reference distribution. So because this is the one that I'm going to use for the rest of the computation. So the reference distribution itself is guaranteed to be symmetric because I averaged over the orbit, right? And because the original distribution is actually approximately symmetric, so therefore after I do the average, that should also be close to the original one, right? Okay, so these are two important properties. It's very simple, come from the average. But now the main idea is that what we're going to do is that we're going to leverage the continuation methods. Instead of continuing all the way to the case where the temperature is equal to infinity, which is very far away, which is corresponding to this picture. So suppose this is what I want to sample. But beta equal to 0, the uniform temperature is kind of like in the middle, right in the middle of the probability simplex. Right? It can take a long way for you to continue over there. But what we're doing here is that starting from the original distribution, by doing this averaging, here the G doesn't quite work out. You see that the two sides don't have the same volume, right? But if you do the averaging, for the reference one, the G actually exactly is symmetric. Okay? So what we're going to do is that instead of continuing to the middle, which is really far away, we're going to continue to somewhere close by. And this close by point is the one that I calculated. This is the reference. Okay? So the whole idea is that before this, we were mostly thinking about let's just continue to the infinite temperature. But infinite temperature is very far away. So that's why we have to do a lot of work. But if we can find something symmetric and nearby, and this continuation path is much shorter, so we can be more efficient. Okay. So that's the main idea of the whole thing. Okay. And I can stop here, but I can go into a little bit more detail. So now I'll talk about how do we combine with these continuation methods. Okay. So I have to give you this gets a little bit technical, but I have to give you two examples of continuation methods. The first method is I'll give you is called annealed importance sampling. So this is what before this project, which typically is being done, for example, is that what you do is that, as I said, you're gonna starting from your target distribution beta, you will have a continuation path go all the way to beta equal to 0. This corresponding to the highest temperature equal to infinity. And then what you also need is that you need something called a detail balance, which is the transition such that satisfy this detail balance condition at the temperature beta L. Okay, this allows you to do this the jump at that temperature smoothly. Now the AIS, annealed importance sampling, what it does is that you're going to sample an initial state S half. The reason why I put a half here, you will see because this state will be shared by two adjacent temperatures. You're going to sample this from the initial temperature, which is beta 0, which is beta 0 equal to 0, so the temperature very high. Now, because the temperature very high, so this step is very easy to do. Okay, you just do Langevin, for example. And then what you do is that every step, you're going to gradually use these transition maps, the detail balance TL maps, going from one state to another. You just keep it going to the next one. Every time you're going to use a slightly different transition map. And at the end, you're going to compute this weight. And magically, this weight will guarantee you such that if you take the final state S with this weight, this will give you adjusted with this weight, this will sample the target distribution perfectly. Okay? So this is the work by Redford Neal about, I don't know how many, 27 years ago, maybe. So this is a very nice idea. Okay. There's also another similar line of work called the Jaginski equality, which is come from the physics community, which is exactly doing the same thing. But I'm using the language of the statistics, which is a little bit easier here. Okay, so now how do we combine the AIS with this symmetric reference we constructed? Again, this picture here. So the idea is very simple, is that instead of starting from right in the middle, sample from the infinite temperature, what we do is that we try to sample from this symmetric reference. Why the symmetric reference is easy to sample? Because I told you, because it's being symmetric. So therefore, I can have this jump between the modes, right? The initial 1 over, you remember this thing? Maybe I can write it here. You have the jump TST is equal to 1 over G minus 1 if T is equal to GS, right? The initial jump, this works perfectly for the symmetric distribution. So this will allows, this step is sampled very easily. And then the rest of the calculation is exactly the same. I don't need to change anything because the whole framework is the same. The second method is called a temper distribution. The temper distribution is another idea, which essentially that instead of going from infinite temperature to the target temperature, what it does is that it tries to construct some kind of Markov transition by, again, changing the temperature. So it's going to start from the, so it's actually a path which is going up and down. So it's going to start from the target temperature, but go to the very high temperature or very low inverse temperature, beta equal to 0, and then come back. So what the algorithm does is that you're going to start from the initial, this will be one step of the Markov chain transition, okay? So you're going to start from a state S of your target distribution, as target temperature, and then you're going to do this detail balance transition. We're going all the way to the very high temperature. And then from the high temperature, you're going to go back to the low temperature. Now, at the end, you're going to calculate this weight and use this to a Metropolis-Hastings rejection step. And if you succeeded, and then you move to a new state, otherwise you stay at the original state. So maybe it's not a good idea to running all the details, but the idea is if you look for temper transition, and this is exactly what it does. Maybe this picture to give you a little bit better idea. So the temper transition says that you're going to start from your original temperature, original distribution. You're going to gradually move on to your target distribution, and then you do a transition of your target distribution, your easy distribution, and you move back. Okay, this is like the U pass. Now, we can combine with this temper transition idea with the symmetrical reference. So instead of going from target temperature to zero temperature, infinite temperature and go back, what we do is that we're going to go from this target density, go to reference density, and then go back. Okay, it's just like we take a much shorter path. Instead of going to the center of the probability simplex, we're just going to somewhere close by, which is equally good. Now, the main idea is that everything is exactly the same, except at the middle level L, right? Previously, we use infinite temperature, so therefore we assume some Langevin can sample very quickly, so which allows us to do the transition. But here, we replace this Langevin with this random transition, which I write right over there. Okay? Because your target is your reference distribution is symmetric, so this will work well. And the rest of the calculation is exactly the same. Okay. Now, I think I'm doing okay with the time. I have 5 minutes left, so I just try to give you one example to show you that this actually works well for very high-dimensional problems. So the problem we consider is an IC model on the rectangle axis from -1 to 1. So, but instead of making the problem fully symmetric, I'm discretizing this domain with a lattice which is not n1 is not equal to n2. So for example, you can think about the lattice I have the examples I'm going to show you is that I have 32 points here and 30 points here. Okay. So it's a lattice which is, for example, which have more grid points in the horizontal direction. And to make the problem really have this approximately is I'm considering the case where you specify interesting boundary conditions, meaning that you're going to specify -1 boundary conditions on these two sides and +1 minus conditions here. Okay? So therefore, it's a spin system, but with the boundary condition fixed in a kind of like interesting way. Now, and the log density, which is the minus of energy of this problem, is given by here. You see that whenever two spins are nearby each other, I have the term SISJ, so the spin like to align with each other. But when it's close to the boundary, it has to be tried to align with the boundary condition you specify. Okay? So with the temperature actually pretty low, this whole system will have two dominant profiles. The first profile you see is that it's going to be mostly black, -1. But near the boundary, it's going to be keep to be +1 because the boundary condition enforces to be +1. Okay? And there's another dominant condition profile is that it's going to mostly be 1. Okay? There's a big channel 1 going from the top to bottom. But near these two boundary conditions, which is specified to be -1, I will have a bunch of black, which is -1 items. Okay? Now, clearly you see that there's some kind of like approximate symmetry here because whenever I have this configuration, I can just rotate it and also flip the sign, I get this configuration. So this is the approximate symmetry I'm talking about. Okay, now, but how do you actually explicitly write down this approximately? Okay, so this is a little bit tricky. So the idea here is the following, is that first I'm going to introduce a mapping. This is involution between the indices. So what I'm going to do is that I'm going to do a 45-degree flip about the location of these indices. Then I'm going to try to find a map, which is an involution on the location of on the indices, such that I map yi, the image of this map of the spin location I to the x of gi. So this is kind of like a condition for g. So I need to find the g this way. Now, once you find the finding of this G use a little bit of optimal transport, but it's very easy. You don't even need such a fancy language. But at the end, what this guarantee is that starting from the index I, if you flip it, you look at the boundary condition over there. That's actually equal to minus Fi, because I do flip it from the horizontal side to the vertical side. Okay. Now, once I have this involution, this kind of like the group action on the locations, I can lift this group action from the locations to the spins defined on these locations. Okay? So what I defined, for example, is that what is the identity map applied to the configuration? It's just keep the configuration itself. What is the identity map applied to the configurations? G applies to the spin configurations. Well, it's going to add to the location Gi is set to be minus Si. Okay. Now you can check that this is actually this G that we just constructed is in fact is a proxy symmetry on the whole state space of this IC model. So this is the calculation to convince you that everything goes through. Okay, so you see that EGS is equal to ES. Okay, approximately equal to ES. Now once you have that, I can do the orbital averaging. So if you here the group has only had two sides, so averaging is very easy, right? It's identity and G. So you're just averaging the action of these two orbits, and you see that after I do the averaging for the reference log density, it actually takes a form which is very similar to the original form of my spin system. The only thing changes is that the only thing that has been changed is my forcing term on the boundary is slightly being changed, and also the other thing has been changed is that my connectivity matrix is being changed. So this picture shows you that what is the involution of the G. The red points is map snap to a nearby blue points. And this tells you the new connectivity of this matrix, which is slightly more complicated than the original horizontal nearest neighbor connectivity, but it's very similar. Now, this is what we combine with AIS with this symmetric reference. You see that it's actually going to try to have the one bunch of paths which sample the all positive dominant configuration. There's many other paths sample the negative dominant configurations. You can check that at the end that the probability of the +1 dominant profile versus -1 dominant profile is about 49 versus 1. Okay? So in fact, what this shows you that even at the same temperature, but just by increasing the lattice size a little bit on one side is actually going to have a pretty significant effect on the relatively probability of these two modes. And this picture shows you how to combine this our work with the temporal distribution. This is I run about 100,000 different iterations, and all these jumps correspond to the jump between two different modes. So this is all +1 dominant profile, this is -1 dominant profile. And you can do the calculation, and this temporal transition combined with our method also tells you that the relative ratio is about 49 versus 1. Now, using this method, you can see that there's about 36 different successful transitions between these two metastable states. But if you don't use this, you will not see even one transition. You don't use our method, use like some other method, you will not even see one transition for a very long trajectory. Now with that, I'd like to conclude, and the main idea is that, I talked about the main idea, so it doesn't make sense for me to go through it again. The one thing I want to emphasize is that the reference log density typically has a very similar structure compared to the original one. So whatever methods, for example, Langevin, Gibbs sampler, Swenson and one that you can use for the original one, you can also use it here. Okay? So that's why we want to work with log density rather than work with the density itself, because log density typically have a very simple algebraic form. And future work, we can try to do that with simulated tempering, parallel tempering, and also what about continuous symmetries? And here we should consider Lie groups and average over Lie groups. Okay. Thank you.
Thank you.